Good day, dear colleagues. My name is Hector Vega-Carrillo, and in this occasion, I want to present the work Spectra and Gamma Factors for X-ray for Diagnosis. This work has been carried out by the collaboration of Guillermo Eduardo Campillo Rivera, Joel Vázquez Bañuelos, and Mayra Guadalupe García Reina, all of us from the Universidad Autónoma de Zacatecas in Mexico, and with the Professor Marcial Vázquez Arteaga from the Universidad Señor de Zipán in Peru, and Claudia Angélica Márquez Mata from the Instituto Tecnológico de Aguascalientes, also in Mexico. All of us want to thanks to the King South University to host this important scientific event, and particularly we are grateful with the chairman and the organizing committee of this fourth international forum on advances in radiation physics for giving us the opportunity to present our work. The motivation of this work is because all living beings are exposed to ionizing radiation that is produced by anthropogenic activities, also known as artificial sources, and by natural sources. The uses or in medicine of this ionizing radiation contribute the most to exposure. And within the medicine, the largest contribution is due to the use of X-rays for diagnosis. Most of the studies focus on the dose at the entrance surface in the patient due to the primary beam, and on the other hand, the leakage, scattered out, and radiation self-absorption received much less attention in the scientific community. Well, the outline of our talk is an introduction where few scientific facts are going to be presented, and we are going to define the objective of this work. Then we will show you the materials and methods that we used. We will present the results, and some of them are going to be discussed. And we are finalizing our presentation with few conclusions. So radiation is the energy propagation and production as electromagnetic waves or subatomic particles through matter. And in terms of electromagnetic waves, we have a large family of different electromagnetic waves that are characterized by the frequency, the wavelength, or the energy. And the main features of all this family of electromagnetic waves are that all of them travels to the speed of light in vacuum. They don't have mass and they don't have electric charge. One group of these electromagnetic waves are named non-ionized electromagnetic radiation, and the other group are named or characterized by the feature of ionized matter, and we name it ionizing radiation. What it means that the energy of this group is large enough to rip off electrons from the atoms. In terms of the ionizing particles, the main feature are due to the mass of the particle, the kinetic energy, and the electric charge. In some of these ionizing particles are the alpha particles, beta particles, electrons, and light or heavy ions. From the exposure that we receive, 82% come from natural causes. One is the cosmic rays, and the other are geogenic. And 18% are due to the artificial sources, different sources of ionizing radiation. And you can notice here from this 18%, the majority correspond to the uses of ionizing radiation in medicine. 21 is due to the nuclear medicine, and 58% are due to the use of X-rays. In medicine, we treat cancer using radiotherapy, and there are two modalities, the brachytherapy and the teletherapy. In brachytherapy, we use the natural cavities in the body to insert radioactive sources. We also can do that applying some surgery to insert these radioactive sources that are named like seeds in order to deliver the larger dose in the tumor and the lower dose in the healthy tissue that are in the vicinity or are nearby the tumor. When we use teletherapy, the radiation is applied from outside the human body, and we can use photons or electrons in these machines named linear accelerators. Or we can use protons also produced in accelerators, or we can use neutrons produced in nuclear reactors or with neutron generators in the technique named boron neutron capture therapy. In medicine, we use compounds that are labeled by a radioisotope that is used to produce images that help to the specialist to make a better diagnosis, or we can use these compounds, labeled compounds, to make studies dynamic and or static, or we can use these compounds to directly fight against the malignancy in some part of the body. When we use X-rays to produce images to make the specialists do a better diagnosis, we can find different types of machines. Some of them are very common in hospitals, allowing to obtain radiographies of some part of the body. Other are small machines that are used for dental radiographies or to obtain panoramic images. Or we can use another more sophisticated technology in order to obtain three-dimensional images of the inner parts of the structures in the human body. All these machines have in common the X-ray tube. And we can see there are very simple designs of X-ray tubes, or another are more complex, but the main parts, regardless the complexity of these designs, the main parts of an X-ray tube is the cathode, where the electrons are produced, and is the anode, where is the target. And in order to accelerate the electrons against the target, we use high voltages. So these electrons, when they collide with the target, they can be deviated in very small angles or very large angles, or completely backscattered. And in these collisions, the energy that is lost by this deviation of the electrons are converted or transformed in photons with lower energy or with high energy. Also, the electrons can collide directly with one of the electrons in the inner shells of the atom, and the electron is ejected, and a vacancy is left here. So one electron from the upper shells tends to fill this vacancy, and the difference in the energy from one orbit to the other orbit is transformed in a discrete energy photon. Therefore, the X-ray spectrum has two components: the continuous spectrum due to the bremsstrahlung of the electrons, and the discrete component due to the type of target that we are using. Also, the spectrum has the N energy that depends on the high voltage that we use to accelerate the electrons. But why is important the X-ray spectrum? Well, the spectrum, knowing the spectrum allows to calculate the total fluence rate, also allows to calculate any dosimetric quantity. The only information that we also need are the fluence to dose conversion coefficients, and if this fluence to dose conversion coefficients are the kerma, so using this integral we can calculate the air kerma. If these conversion coefficients are those related with the ambient dose equivalent, using this integral where the spectrum is included, and we come out with the ambient dose equivalent and any other dosimetric quantity that we want to calculate or to determine. When we use the main beam to expose the human body, I mean to obtain an image for a diagnosis purpose? Well, the main beam collide with the surface of the body, and when this phenomenon is happening, some part of the photons will be absorbed in the entrance surface. Some of them will be transmitted to the body, and those photons that are inside the body, that are being transported inside the body, some of them will be scattered to another parts of the body. When this main beam collide with the body, well, some photons will be scattered out, reaching other parts of the whole, and also there are will be another set of photons that leak out from the X-ray tube head. So these scattered and leaked photons also reach another part of the whole. So during the operation of X-ray unit, more attention is paid to the useful beam or direct beam, but much less attention is given to this scattered out and leaking out X-rays. Having this information of these photons allows to, in the clinic, allows to design and review the protocols of radioprotection for patients and staff. Also, this information is useful when you want to design or to evaluate the barriers of the room where the X-ray unit is allocated. So the objective of this work is to estimate with Monte Carlo methods the X-ray spectra produced in 70, 80, 90, 100, and 120 kilovolts X-ray tubes having tungsten, molybdenum, and rhodium and aluminum filters, and to calculate the gamma factors for air kerma and ambient dose equivalent. The materials and methods that we used was Monte Carlo methods through the MCMP5 code, and with this code we designed the model of the X-ray tube, taking the technical information of this commercial X-ray tube. We changed the target, and we use the three materials that are more common in the X-ray tubes that are used for diagnosis purposes, which are tungsten, rhodium, and molybdenum, included in our model the aluminum filter, and also we include the glass that involves the X-ray tube and the light shielding. And as source 10, we use monoenergetic electrons having 70, 80, 90, 100, and 120 kilo electron volts energy. With the model inside the MCMP code, we simulate the transport of the electrons through the target and the X-ray production in the target and the transport of the X-ray outside the X-ray tube along the useful beam, and take into account also those photons that leak out from the X-ray tube head. With the spectra, we calculate the gamma factor for the ambient dose equivalent and the gamma factor for the air kerma to 1 meter from the focal point along the useful beam, and take into account the leak out photons from the shielding of the X-ray tube. Here I'm presenting you the model that we use, including the lead shielding. We include the glass, we include the target. Here is vacuum, and in this zone in green represent the atmospheric air. Also, our X-ray tube model has the window where the main beam pass through, and we include the aluminum filter. In order to calculate the spectra, we also include several detectors, point light detectors to the F5 tally in the MCMP code. Below the focal point, few centimeters below the focal point, we put the first detector. Then after the glass, we include the second detector, and after the filter, roughly 6 centimeters from the focal point, we allocate the third detector in order to review what is the function, what is the change that we observe with the aluminum filter, and to 1 meter from the focal point, we allocate the fourth detector. This is along the useful bin. Also, to 1 meter from the focal point, we use a point light detector. We call it to the right or in front. Is allocated along the same direction of the electrons, and to 1 meter from the focal point, but in the rear part of the X-ray. We call it back or opposite to the main beam. The result that we obtained from this work, I'm going to present here all the spectra when we use an X-ray tube working to 70,000 volts, having tungsten target, and we can notice that just below the focal point inside the glass, we have this spectrum that contains the larger amount of photons. All of a large contribution are due to the low energy photons. When this spectrum pass through the glass, so the spectrum changes from red to blue, and we can notice that it's a reduction of the amount of photons, and the largest reduction is noticed in the low energy photons. And when we pass through the filter, so the filter eliminates all these low energy photons, and these are the photons in the detector that is allocated just below the filter. And the spectrum that reach 1 meter has this shape, and you can notice that several orders of magnitude, approximately 1, 2, 3, 4, 5 orders of magnitude is reduced the amount of photons to 1 meter. And these two spectra represent those spectra of X-rays that leak out from the shielding of the X-ray tube. And the black one is the detector that is allocated to the right. The green one is the spectrum that is allocated in the rear part of the X-ray tube. Now I want to change to 80 kilovolts, but first let me point out that the endpoint of the spectrum, is related with the voltage that we are using, 70,000 volts. When we change to 80, we barely notice the presence of the discrete contribution, the characteristic S-rays. We observe the same trend, the same tendency as we move from the detector near of the target to the detector allocated 1 meter along the useful beam. And also, we are including here the X-ray spectra of those photons that leak out from the shielding of the X-ray tube. We are going to change now to 90 kilovolts, and you will notice changes in the discrete peaks that become more relevant. You see, we have the same trend, the same tendency, and we notice that the discrete part of the spectrum begin to be more relevant as the voltage is increased to 100 and 220 kilovolts. Now, allow me to show you the spectrum in another fashion. Instead of using logarithmic scale, I'm using here linear scale, and you can see how changing the voltage change the shape of the spectra, and as the voltage is increased, the relevance of the discrete component are more important. If we use those spectrum and calculate the mean energy, I'm presenting you what is the mean energy of the photons produced by the 70 kilovolts X-ray tube in the position 1, in this position, and how, as we move to the different positions, we can notice that the mean energy is increasing regardless the voltage. As we move from the focal point to the detector to 1 meter, the mean energy of the photons increases as well. Here I'm presenting you the spectra when instead of using tungsten, we are using molybdenum. Here are the 70 kilovolts X-ray, and we notice the same tendency that we observed in the previous case, where the production of the discrete component are in different position because now we're using molybdenum to the discrete version of the peaks that we observed in the case of the tungsten like target. This is 70, this is 80 kilovolts, this is 90 kilovolts, this is 100, and this is 120. Notice that we can point out that the discrete version becomes more relevant as the high voltage is increasing. Also, you can notice that the shape of those photons that leak out are different. The spectra are different to those photons that leak out when the X-ray tube has a tungsten target. Now, I'm show you the spectra when the molybdenum target is changed by rhodium. This is the case of 70 kilovolts, and we notice the same trends, and we notice the presence of the discrete version, but now are allocated in different positions than the previous two targets. This is 70 kilovolts, this is 80 kilovolts, this is 90 kilovolts, 100, and 120 kilovolts. Now, allow me to put all this information in numbers. So in this table, I am presenting you the gamma factor for the ambient dose equivalent to 1 meter from the focal point for the focal spot in the useful beam. And here is the information when the target is tungsten, when it's rhodium, and when it's molybdenum in terms of the high voltage. Notice that the gamma factor are expressed in terms of millisievert square meter, milliampere per minute. The minute, it means the time in minutes that the beam, X-ray beam is on. The milliampere are the current that we use in our X-ray tube. A square meter is the distance in meters from the focal spot to the point of interest. And those are given in millisievert because we are expressing here the ambient dose equivalent. And regardless the voltage, doesn't matter which voltage you choose, we can notice that this gamma factor are reduced as we move from one target another. The larger is due to the tungsten, then the rhodium, and then the molybdenum. The probable explanation of this is probably due that in this direction, the atomic number and the density of tungsten is larger than rhodium, and these quantities are larger than the molybdenum. So as the atomic number decreases and the density decreases, these gamma factors, regardless the voltage, also goes from a larger number to a smaller number. Also, we can notice that regardless the type of target, as we use larger voltages, the gamma factor also increases. This is the case of gamma factor for the ambient dose equivalent, and this is the case of the gamma factors for air kerma. We notice the same tendency. Regardless the voltage, the gamma factor for air kerma will be reduced as the atomic number and the density of the target is reduced. Also, regardless the type of target, we can notice that as the high voltage increases, the gamma factor for air kerma also is increasing. Now, in order to emphasize the importance to use the spectrum, allow me to present this information. If I want to calculate the ambient dose equivalent without having the detailed information of the spectrum, we can use this approximation. I can calculate, or I can look in the literature the mean energy of different spectrum, and with this mean energy, I look for the ambient dose conversion factor, in this case for the ambient dose equivalent, and I multiply this value by the total fluence. This is one way to calculate the ambient dose equivalent. The other way is using the X-ray spectrum and all the dose conversion coefficient, and doing this integral also allow me to calculate the ambient dose equivalent. If I compare the ambient dose equivalent divided by the total fluence, so I obtain the conversion, the fluence to conversion factors for the ambient dose equivalent of the kernel in air using the spectrum. We call it here KAX and H as dot X. And we can notice that when we use the spectrum, ambient dose equivalent and the air kerma are larger than the values that are tabulated in some of these NCRP reports when we use the mean energy. So using the criteria of using the mean energy of the spectrum, because we don't know the details of the spectrum, we underestimate the dose in comparison when we use the detailed information of the X-ray spectrum. So here I'm showing you the gamma factors for the ambient dose equivalent in both cases, but due to the X-rays that leak out from the shielding of the X-ray tube. In the front, which is 1 meter from the focal spot, here are the values, and we can notice that as the voltage is increasing, also the gamma factors for these leaking out photons are also increasing. Also, we can notice that if we change from tungsten to rhodium and from rhodium to molybdenum, this gamma factor decreases. Notice here that the units are in microsievert, which means are three orders of magnitude lower than the gamma factors that is obtained in the mean or useful beam. Also, the same trend, the same tendency is noticed when we use the detector allocated in the back, and we notice that as the voltage increases, the gamma factors also increases, and that this value changes in function of the type of target, being the largest for tungsten, then when we use rhodium, and then when we use molybdenum. Here I'm presenting the same information, but now is the gamma factor for obtained from those photons that leak out and reach this point, this detector. And in this plot is the gamma factors for the air kerma for the detector that is allocated in this position. We also notice the same tendency, the same trend. So as conclusions, we can point out that the over-calculated spectra show both contribution, the discrete and the continuous contribution. Also, that the X-ray spectra depends on the target type and the voltage, and that the spectra endpoint depends on the voltage that we use, that the glass and the filter eliminates in a large amount the low energy photons that do not contribute to the image, and that these photons could reach the skin, can produce a serious damage, because having low energies, all these photons will be absorbed in the patient skin. So the use of glass and filters eliminate these undesirable low energy photons. Also, we can conclude that regardless the target, both dosimetric quantities, the ambient dose equivalent and the air kerma, increase as the voltage increases. That the gamma factors along the useful beam and those gamma factors due to the leak out photons are larger as the atomic number and the density of the target increases. And finally, that the use of mean energy underestimate the dose. What is the advantage of using the gamma factors? Because in a very simple expression, the gamma factors for ambient dose equivalent or air kerma can be used to obtain the ambient dose or the air kerma, only knowing the current of the X-ray tube and the time that the X-ray beam is on, and only we need to define at what distance from the focal point we want to know the ambient dose equivalent or the air kerma. So with this, I finish my presentation. I want to thank you for the generosity of your attention. Have a nice day.